Okay, I guess I'll start. Um, so, um, for those of you who haven't already, hopefully you will have logged into Zulip and you have access to the stream because you DM'd me and then I said, yes, here's your access. If you haven't, reminder again, do that. So you should get Lead and Method installed and you will have gotten the course repository, which is this TPIL 25 repository on my GitHub. And if you have any problems setting up those things and getting the highlights on these files, then let me know. You can always find me anytime after class. Okay, I also wanted to mention some questions, some which came like immediately after the class or the next day or something like that. So one thing is I totally forgot that we should be having a break because it's a long class. So from now on, we're going to be having a break at 13:50, and if I miss that, then someone remind me so that I can let you all go. And then we'll be back here at 14 to continue. Another thing is that sometimes you might notice that this first line here gets highlighted in blue, and then there'll be some bit of text here saying that you should run the restart file command in your editor. This occurs when there are files that have not been compiled, so like your dependencies have not been compiled. So it's talking about the restart file button, which is down here in the right-hand corner. The people watching on YouTube won't be able to see this because it's covered by my face, but trust me, there's a button right here. Well, that's one thing, and you can click that button in order to get it to build dependencies. However, in this class, you're probably not going to want to do that because if it says that it wants to build mathlib, then that probably means that you don't have mathlib pre-built. And so in the instructions, when you get this in the README, it is mentioned that you should run this lakeexe cache get, and what this does is it downloads mathlib so that you don't have to build it. Building mathlib takes something like an hour, so no need to do that if it's not necessary. Also, if you don't want to use the command line, you can also find this as project fetch mathlib build cache, and that will do the equivalent of this line of code. Okay, so today I'm going to tell you about how to actually write proofs in Lean, and also sort of the basics on tactic mode. So I mentioned yesterday, or on Tuesday, the def command, which is used for making a definition. So you say an expression, you give its type here, and then you give it a name, and now you can use it like this. So you can see that foo has now been entered into the environment as a natural number. And also that it has the value 1 because if we run it, we see that it gets a value 1. Now, because of propositions as types, which I mentioned on Tuesday as well, you can do basically the exact same thing that you would to define a number like 1 as a natural number. You can also define an element trivial of the type true, and so this is effectively a proof of the theorem true. So there's another keyword called theorem, which is basically the same as def. It's conventionally used for when you are defining proofs, like constructing elements of propositions. And it does actually ensure that you are only defining things of proposition types, so you can't do the equivalent of this here. But other than that, they're basically the same. Okay, so let's actually see what it's like to construct a proof term in stages. So, for instance, here we have a proof. We have a goal. We have the intent to construct an element of this term true implies true and false implies true, right? And so one way that we can do that is we can just write down a term here. So I can put an underscore, and when I put an underscore, it gives me an error. The error is informative. It tells me it does not know how to synthesize placeholder, and the context is this. It's basically saying, you're not done yet, this is the goal. So we can make use of this in order to sort of work on the pieces of the goal. So here what I did was I see that the goal is a conjunction, and so I want to construct a conjunction. So I write this angle brackets, and now we have two parts to this thing. So I want to give the first component and the second component. And I put more underscores in here. If you don't put anything in here, then you're going to get lots of syntax errors and other things like that, and you're not going to be getting very informative feedback from the system. So I always recommend that you put in at least an underscore here in order to make everything syntactically correct. And now the errors are of this more useful form where it says, don't know how to synthesize placeholder for some particular argument, and it's saying, okay, the goal that remains is to prove true implies true, and then there's another one that's proving false implies true. So this is a function type, so I can introduce a variable called h, and h has the type true. I could write h true like that also. And now we see the expected type says that h is in context because I introduced this h here, so we're just constructing an element of type true. So for instance, I could use h here, and then that works. And then here, for false implies true, let's do something slightly different, and we'll just prove it using trivia. So this usage of underscores to sort of build out pieces of a proof incrementally is what I would call sort of hole-driven development. We are just writing the proof term, leaving holes in it, refining those holes, adding more and more information until we have the complete proof term. When you look at the final result, though, it doesn't really have any of that evidence that it went through that process of iterative refinement. It's just the final proof term, so we end up with something that looks like this. Since this false implies true, there's actually a second way to prove this. We could prove that false is impossible to inhabit, and you can do that using this no fun, because this is like an empty pattern match. So this is introducing a function and then an empty pattern match, and it's no fun. Okay, so here's a more advanced example. So we have a goal here where we have a bunch of stuff in context. We have P of A, we have for all x, Q of x implies Rx, for all x, Px implies Qx, and we can sort of build this out iteratively where we say, okay, H2, if I write H2 alone, it complains that H2 is, it's for all type, we have to apply it first to x, which is something, and then we have to apply it to q, which is something else. Now, I put two underscores here, and now it's giving the sort of the good error. It's giving an error that says, I just don't know how to fill in this thing. You'll notice there are two underscores, but one of them was filled in automatically because it knows that in order for H2 to apply to two arguments, this thing has to return R of A. So it actually knows that this is A. Like if I put in 0 here, it wouldn't type check, right? It's got to be A. So it's actually filled that in, even if I just leave it as an underscore. And here we can do it again. We apply H1 and give it two underscores. And now this subgoal here is P of A. So H3 is of type P of A. So this is just another example of how you can sort of iteratively refine yourself to a proof of an expression just in pure lambda calculus here. So now I want to show you how to do sort of the same thing but with tactics. So the way tactics work are, there's you start with by, you write by, and then you give a tactic block, And this whole thing is an expression. Just like this h2 whatever thing, this is an expression. By of all this stuff is an expression. You can use it anywhere where expressions are allowed. You can use it inside the types of things, anywhere you want. But when we use it here, what it does is it basically puts us into a mode where we can see that as a tactic state, the type of the thing that we were expecting. So here, we're expecting R of A in some context. So if I say by and, I'm going to put done in here, but done is a tactic that just fails if there are goals. So it just errors, but I'm using it here so that I don't have an empty sequence of tactics, which is a syntax F. But okay, so it wants to supply, like, if we want to do the equivalent of this proof here, we can use the refine tactic. So refine, you give it a partial proof. So here, for my first step, I wanted to do like this, h2 and then 2 underscores. Now, refine has a slightly different syntax in that it wants you to use question mark underscore for the sub-goals. So underscores are the ones that can be solved automatically, and question mark underscores are the ones that are going to be the next line of the proof. So here I wrote h2, apply it to A in this case, and then give me back this last bit as a sub-goal. So you see on the right-hand side, before I apply refine, my goal is R of A. After I apply the refine, the goal is Q of A. So using h2 here, which goes from Q to R, we're sort of working backwards. So we now have Q as the goal. And so we can do the same thing applying h1, and now the goal has gone from R to Q to P. And we can finish the goal by applying h3. And now the done tactic is done. So, okay, a couple of variations on that. So we can also, instead of using refine for this last one, we can use exact. Exact is basically the same as refine, but it doesn't generate subgoals. It enforces that it always has no subgoals. If we tried to use it here, it would just complain that this question mark underscore is trying to create a subgoal. Apply is similar to refine with a bunch of underscores. So it basically adds in underscores until it can't add underscores anymore, and then it returns all of the subgoals that haven't been solved yet. So here, we can write this, but we can also just leave off the underscores, because it'll figure out that this thing is applied to 2 arguments, and it generates 1 circle. And so we can just do an apply-based proof here.
Isn't exact a bit redundant, or when do you want to use it?
I mean, exact, you mean with refine. Exact is basically a special case of refine. So yes, it's redundant, but it does come with this additional assurance that it doesn't generate subgoals. So sort of syntactically, just by looking at the proof script, you can tell that's the end of that line. And you don't have to worry about it generating 4 subgoals that are then handled later or whatever.
But I thought I anyway have to mark subgoals with a question mark. Or is this not always true?
This is true.
Two meanings.
Yeah, I mean, it's absolutely true. You would have to look through the text for the question mark. I mean, if it's a big term, maybe this is more difficult. It's slightly more declarative. But yeah, they have a lot of overlap. And this is a bit of a, well, there are a lot of tactics that you can use. There are many ways to solve goals in Lean. And I'll give you a smattering of tactics here, but there's a ton more that I won't be able to get to. Okay, so if you're interested in seeing that, so here we had apply do something, and then if we were wondering like, okay, what did apply actually do? Can we turn it into the equivalent refine? Well, there's a tactic for that called show term. So if I apply show term to the apply tactic, so it's the same proof as before, but now we're gonna do show term, and you see that it outputs refine H2A question mark. So basically the exact same proof as before, and this is sort of just the equivalent, showing what that line did. And this can, I mean, in the case of apply, it's not doing a whole lot, but tactics can do very complicated things, as we'll see some later, and show term allows you to just see the proof proof term that was generated for anything. So that's nice. Assumption, I haven't mentioned assumption yet. So assumption is here the goal is P of A, and we have a hypothesis which is P of A. So if we call assumption, it just looks through the goals, through the local context in order to find something that is exactly the same. And if so, then it matches. I have forgotten to plug it. Any questions?
Was there any like keyboard shortcut you were using to go from short term to refine there?
Yeah. So there are actually a couple ways that you can do it. So one thing is there's this big blue light bulb here that has a quick fix that says try this, refine, whatever. And then if I click on that, it replaces it with refine. The other thing I can do is that this is a button. I can click on this and it replaces the text as well. So yeah. Anytime you see try this, it's generally making it's generally doing the same thing. It generates a thing that you can click on and replace the text. And it also generates one of these light bulbs. By question mark is a shorthand version of show term, which works on an entire proof block. And here, by question mark has given us the entire proof term. So we can just replace the whole thing with the term mode proof, which looks basically like what we were doing before. Okay, so I showed you have works inside and outside of tactic blocks. So have in term mode looks like this. So you're just constructing a term and then using it, and this turns into some kind of lambda abstraction and then application. But it also has a version where you just use it as a tactic, and it changes the goal to add things to your context, and it unwraps to exactly the same piece of proof term. Here we have an example with nested have. So this is basically doing forward reasoning. So here we did backward reasoning, right? We started from R of A as our goal, and then we applied H2, which reduces the goal to Q of A. And then we applied H1, which reduces that goal to P of A, and then we finished it with H3. But we could also go the other way around. We'd say, okay, we have H3, that's P of A, and we also have H1, that's P of X implies Q of X, so therefore Q of A holds. And then, because Q of A holds, also R of A holds, and hey, wouldn't you look at it, that's exactly what our goal was, so we can finish. So that's sort of what we can do here. So we say, okay, Q of A holds by applying H1 to H3. And then R of A holds by applying H2 to HQ. And we named this intermediate assumption HQ. And then inside one of these things, you can go back into proof mode. So basically, you can do forward and backward proofs in arbitrary intermingling. And then also, when you don't name a have statement, its implicit name is this. So it's as though I wrote have this.
But if you have multiple unnamed have, will you be able to use only one of them?
So if you have multiple unnamed haves, they will all be named this, and the later ones will shadow the earlier ones. Now, shadowed hypotheses will be shown with a dagger in the tactic state. You can see them like this. And so you can't refer to them directly. However, that doesn't mean that they don't matter, because they can still be accessed by things like assumption, for instance. So they are still in your context, but they just don't have names that you can refer to. And there are also ways to rename the things in your context to give the names back to you so that you can access them. Okay, so here's a different example. So now we have, this has multiple subgoals. So here we're trying to prove P and Q and P, and we're going to do so by applying and intro. So and intro is just, if you have A and you have B, then you have A and B. So if we apply and intro, it actually generates two subgoals. So you can see, to start with, we have one subgoal, that's P and Q and P. After applying and intro, we have two subgoals. One of them is P, that's the left part, and the right part is Q and P, because this is right associated. So the left part we can prove by just applying HP, and then the right part, we do the same thing again. We have a proof of Q and a proof of P, and that finishes the proof. And we can see if we just print. I didn't mention print on Tuesday, but print is another command that allows you to see the declaration and value of a definition. So you just give it an identifier, and then it tells you about that identifier. So here you can see that the proof that was generated is just pairing up HP, HQ, HP, which is sort of what you would expect here. You can also, this is just another formatting, so like here, so far I've been writing them one per line, but you can also write multiple on a line if you separate them by a semicolon. So just doing the same thing but in fewer steps. Here's some more structured versions of the same proof. So after this apply and intro, we have two goals. And you'll notice that they actually have names. It says case left and case right. And what it's saying is that you can actually refer to those goals, like focus in on case left. And so after this line, we're now focused in on just the left goal, which was to prove P. And on this goal, we're just focused on Q and P. So the same thing here. So here we apply and intro, we get two goals, and then we use this case thing. So this is a way of, when your goals have meaningful names, this is a way of indicating which part is which. You can also use this case thing in order to reorder the goals if you wanted to work on a different one first. Otherwise, you'd have to work on the left one first and then the right one. This is another version of that proof style where rather than just saying case, you just don't mention which case, you just want to work on the first one coming. So this is actually, you can write this either with a dot or with a middle dot. The usual one we use is a middle dot. This basically just focuses on a subgoal and then requires that it be proved. So these dots are sort of unnecessary in the sense that like I can remove them and just have this straight line proof like before. But when I have the dots in, it sort of enforces some kind of sanity check here that like I can't be proving the second subgoal in the first dot. So I have to have another dot if I want to solve the subgoal. So this is nice for just readability of proof scripts. You can see explicitly that like this tactic generated two subgoals. That's why there's two dots here. This tactic generated two subgoals. That's why there's two dots here. And this one was closed on this line. That's information which is lacking when you look at this version of the proof. And this is, again, just showing assumption. So here we're using HP and we're using HQ, and maybe we, don't want to be so specific about it and just say, they're in there somewhere. So we just use assumption and then it picks them out. And we can make this even more generic by just using constructor. So constructor is a tactic which says apply the intro for the type that I'm looking at. So in this case, the type we're looking at is an and, the goal is an and, so let's apply the introduction rule for and. If it was an exist, we'd be applying the introduction rule for exist. If it was an or, then it would apply the left one, it would apply the first one that works. in some cases, when you have complicated inductive types that overlap in weird ways, it might be the case that even if it has multiple constructors, only one of them will apply in a given situation, and so this sort of does the right thing. Okay. Oh yeah, so intro is sort of the equivalent to the term mode function arrow. So before we had, let's go back up here, I'm looking again at this proof that we did before of true implies true and false implies true. If I want to do this function introduction thing, where we originally our expected type was true implies true, and then we go in here, and now that we introduce the left-hand side, it's H, the right-hand side becomes true. So the equivalent of that in tactic mode is called intro. So here, our goal is true implies true. We use intro, and now we have H of type true, and then our goal is to prove true, and using assumption, we're going to use this H here. So this is the same proof, and we can actually see this using this by question mark thing that is actually generated the same proof term as the one that we wrote down before. Okay. Any questions?
If I have an underscore, is there a way, and it's solved, is there a way to get this through the IDE into my source code? Like,
If you have an underscore,
but it's kind of solved.
but it's solved. Oh, we had a couple examples of this before. Like this. Like this one here is solved. This is actually A, and you can see it's A because when I highlight it, it says A. But there is not a command to just like insert it.
But I assume show term should work still.
Yeah. I think if I do show term on a refine, it will suggest a refine, which has the A in it. So yeah, that's a way to do it. Okay. And this is a more elaborate example. Here we're showing one of the De Morgan's laws. No, not. This is distributivity of and over or. So if and only if is it has two sides, so we have to prove it using the introduction rule for if and only if. We could also use constructor here. If I can spell it right. And then we get a goal, which is we get this left thing, and then we want to prove the right thing. Or lim is just the eliminator for or, so we have an or, and then we have to prove given A, given B. So I won't go through this whole thing, but this is basically applying primitive rules for or elimination, and right here is just getting the left and right side of and or in left, so this is like left injection, so if you're given A, then you have A or B, and then there's or in right as well. And so you can construct a proof of this propositional logic thing using this method. And this is, this is somewhat verbose method of doing it, but it's very much sort of one step at a time, right? You can, as you walk through these lines, you basically see exactly, all the things in context, and you're working down towards, oh, I have to prove P. Where do I get a P? Well, there's one over here, so I can use and left of H. Where do I get a Q? It's in my context, right? And then you keep going, and so on. So this can be nice for like when people are writing a proof for the first time, you're just hacking it out, and you end up with a proof like this. This is a slightly more compacted version of the same proof, using some of these more structuring primitives. So this one is using cases. So cases is replacing our usage of or lim here. So or is an inductive type, and it has two ways of constructing. One of them is the left thing, the other one is the right thing. So h.right is Q or R. So if I pattern match on it using these cases, I get either HQ, which is a proof of Q, or HR. And then in both of these cases, I have to prove the same goal, which is this P and Q or P and R. And then the rest of this is done in term mode because it's just more compact that way, and so on. So it will not be that unusual to see lean proofs proceed in this way, where this is a mixture of term proof and tactic proof, right? Where at the small scale, you're seeing term proof style, and then at the sort of large sort of proof structuring side, we'll see these tactic proofs. Intro has a couple other features, so here you can do multiple intros at once, and that's probably not too surprising. This is doing a proof about transitivity of equality, so you're seeing EQ trans, this is transitivity of equality, and EQ same as symmetry, and we can use it to combine with this. You can also pattern match. Someone asked about pattern matching in functions on Tuesday. You can also do pattern matching intro, basically the same kind of thing. And here we are proving that exists X and in one way is the same as existence and in the other way. By just pattern match, we get the 3 bits out, and then we recombine them into the opposite order. You can also do this kind of pattern match. So this is a pattern match on, well, there's 2 cases basically. So here we're pattern matching on exists of an OR. So if we pattern match on this, we get the X, and then we also get the 2 ways that you can construct an OR. So that's what this is doing. So we have, here we've named it W, and then also the left-hand side or the right-hand side. And in both cases, we have to prove this right-hand side. Show is a tactic which just sort of asserts what the goal is. Now, normally this wouldn't be too useful. Like you would think, well, there's only one thing I could possibly say here. I could only say, and you know, the goal itself, right? I can say, show this, and that works. But it can also be used to assert something that's definitionally the same as the goal, but maybe not like syntactically the same. So in this case, we have n plus 1 equals n dot suck, but then we show n dot suck equals n dot suck, and so you can see that the goal has changed. So this can be used for presentation purposes if you want to have your proof script reflect more of the actual goal. Then you can use this, but you can also use it for being able to sort of force definitional unfolding or other things which might be trickier to do with other tactics, which I'll mention. Okay, let, I mentioned let before. Let exists as both a tactic and in term mode.
So will the definitional unfolding not happen automatically otherwise?
Actually it's not needed in this case because REFL also works up to definitional equality. So some things will care syntactically about the term. An example of this is rewrite tactic, which we'll get to. It really looks at the term and what's visible when it's trying to match things. So doing some definitional unfolding beforehand might be needed in order to get the right things to be visible. Okay, so let is the same as have, except that it keeps the definition sort of in the context. So here exists is, this is basically the same as using something like this. We're going to apply, we're trying to prove an exists thing, and we're going to supply the witness. And then we're just going to close the second sub-goal, which is a plus 2 equals 8, using REFL, which would only make sense if this was 3, if a is known to be 3 plus 2, 3 times 2. If we use have here, this isn't going to work. And so that's why when I use exists here, it doesn't complain because it attempts to do the proof and then it doesn't So it's actually, the proof's still not done. But if we use let, then it is able to close the goal. Okay. Any more questions?
Wait, so with that one, if you wanted to define the term outside the tag, like if you wanted to do a let that was
Oh, like
just
outside the tag, like this?
yeah,
That
that's
works.
the word.
Yeah.
So is let a tactic?
Let is both.
Uh-huh.
Let and have are both outside and inside. So let exists as a syntactic construct like this, where you say let, whatever. This is not syntactically correct. But let and then another expression in term mode. That's how it works. In tactic mode, have doesn't have to take anything after it, but it's just like a tactic on its own, and then it gets followed by more tactics. So we have, and then whatever comes afterwards.
I didn't quite follow. What was the difference between let and have?
So the difference, you can actually see the difference in the tactic state if you look carefully here. So if we have let, afterwards, the tactic state says A of type nat is 3 times 2. In have, the tactic state is A of type nat.
Oh.
So after this point, it's totally forgotten what nat it was. You proved that nat was an inhabited type, but nothing more than that. I mean, obviously that can be useful when these are, proofs of sub-goals or whatever. Like when you're doing, this kind of propositional logic or whatever, you are quite often constructing elements of propositions, and the specific element of the proposition doesn't actually matter. So you'll basically, normally you want to use have, use let when you need to use let, and then that's useful. Okay. Any other questions?
Why don't you have to prove this with refer?
Why don't I? Oh, because exists. Roughly speaking, it does a try-ref a lot. I'll get to that. But, roughly the implementation of exists tactic is like that. I don't know. Okay. Alright, so I want to get to some combinators. So we already saw the semicolon combinator. This is not technically a combinator, it's just two tactics in sequence, but we can think of it as a combinator. So that is to say that the semicolon combines two tactics to produce another tactic that just runs one after the other. But there's other tactics, other combinators that we can use. So here we have a proof of P and Q, where we have P and Q in a context, and we use constructor, and then we get two subgoals, and both of those subgoals can be closed by assumption. So a tactic we have for that is this funny looking semicolon in angle brackets, which, as you can see, it says it runs the first tactic on the main goal, and then it runs the second tactic on all of the goals that are generated. So in this case, we have assumption getting run on both of the two goals that are generated by constructor. So that gives us another tactic, a single tactic. Whereas if we were to just use the semicolon, then it would complain because this would only run on the first subgoal that is generated by constructor, and the second one is still hanging out, and that's why Bai is complaining here, saying that there's still more goals to solve. So first is a combinator which takes a sequence of tactics separated by these bars, and so here it's going to apply the first one that works. So like if we do this in this order, then it's going to try to apply in right, and then it's going to try assumption, and that fails. So then it tries in left and assumption, and that succeeds. You see here actually that it's complaining a bit about how these tactics do nothing, and that's because I'm giving it several cases to try, and this last case is actually never tried. So even if I did it doesn't actually run this code, so it doesn't complain about it not existing or anything like that. So that's why there's this warning here. Okay. Repeat runs a tactic until it fails. So it just keeps running it while it's succeeding, and then the first time it fails, then it stops. And so here we can just sort of find our way through this maze of ORs to try to find something that we can close by assumption by applying left and then assumption, or right or assumption, and just keep doing that in a loop until it's done. And so this is showing how the same exact proof script can be used to close P or Q or R given any of Q, P or Q or R as assumptions. And here we're using repeat on constructor or assumption. So we have P and Q and R that are available, or that we're trying to prove. So if the goal is a AND, then we apply constructor and that'll work, and assumption won't work. Whereas if the goal was a P or a Q, then constructor won't work, but assumption will work. So if we just keep trying the constructor and assumption, eventually we'll get everything. And that's what this proof is.
It's this for now I see.
This is another variation on this AND proof. So we apply constructor. This generates two subgoals. We can't apply constructor again here because that would apply constructor to both of them. And while this one can be split up by constructor, this one can't because it's not a AND. So we want to say like, okay, try constructor, but if it doesn't work, just do nothing. And that's what try constructor does. So try is a combinator which attempts the tactic. If it fails, it does nothing. So we run constructor, we try constructor on all of the subgoals, and now after this point, we'll have 3 subgoals. So just the second part got split, the first part was left alone, and now assumption applied on all 3 of the subgoals in one go finishes all of them. Okay. So all goals and any goals are another way to write this kind of thing. So here we run constructor, and then we run try constructor on all of the goals. So at this point there are 2 goals, so we'll just run try constructor on both of them. And then we run assumption on all of the goals. So this is an alternative to sequencing things with this angle bracket thing. We can just run it on every goal that exists. And then any goals is like all goals, but all goals requires that the tactic succeeds on every subgoal, whereas any goal will only fail if they all fail. So that's why we don't need the try in this case. If we try to use all goals constructor, this complains, but any goals constructor does not complain. And this is a more excessive version of the same example where we just have lots of ands and we split everything, and then so this can definitely save you some trouble if it's just a very long and rote kind of proof. Alright, so
these quantifier, any and all goals, they only work on the goals that I have at the moment, not that are generated by my tactics that I put there.
This works on all of the goals that are there. So whether you generated them or whether a tactic, added more things, just all of the goals that are in this data.
But all goals constructor will also generate new goals, but then they are not recursively subjected to this constructor tactic, right? Because that's why you have to do repeat.
So any goals, if I run it once, in this case, it's gonna peel off one layer of constructors. If I do it again, then it, now it peels off another layer. So we do it like one more time, now we have another layer, and one more time, and now everything is just those, and then if I try one more time, now it fails because everything is an atomic value. So there's not going to be any more constructing happening. So the repeat here is just doing that to all. Oh, and I wanted to mention something about precedence here. So I've been putting these in parentheses, but it's not actually needed. And this is maybe a slightly confusing thing. Repeat and try and any goals and most of these other combinators, they have sort of very long, low precedence. So that means that the thing after them is just, if we have a semicolon, then this is actually going to get braced like this, not like this, which you might expect. So, just so you know, what can I do? Skip. Skip does nothing. I know. So yeah, this is the equivalent to doing this. Okay. Since we're about to start another section and we're about time, let's take a break now, and we'll be back in at the top of the hour.
Can we ask a question during the break?
Yeah, please.
I read later and I'm not quite sure I understand why we need to try. Like if you go back to the example at line 270.
Constructor, so we have this P or Q or R, or and Q and R. So after constructor, one of the goals is a P, and the other one is Q and R, right? So running constructor on all, what this does is it runs constructor on all of the sub-goals that were generated. So it tries constructor here, and it tries constructor here. But the thing is, running constructor on this is going to fail because it's a P, it's not a inductive type, so it doesn't have an intro. Whereas try constructor, it runs try constructor on this, and it runs try constructor on that. Try constructor on this runs constructor, which fails,
But try
so it does nothing and succeeds.
Okay.
So try never fails.
So here you're basically using constructor like for the side effects
Mhm.
of like breaking a goal into more.
Well, it succeeded on the second goal.
Yeah.
In the first goal, it didn't succeed. But I just want it to ignore the fact that it didn't succeed and just keep going anyway. And so that's what tries to.
So the concept of like a tactic failing, it means it failed to like reveal any new goal.
Yeah, so tactics, the output of a tactic is, you can think of it, lives in some exception mode. It can just throw exceptions. It's trying to generate new set of goals, but it didn't. Instead, it just throws an error, and try catches that error, and then it reverts all of the state changes that happen and produces basically a no-op. So no matter what happens to the tactic, if the tactic doesn't throw, then it just does whatever that tactic does. But if it does throw, then it just resets its state.
I missed, what was it that the intro tactic does?
The intro tactic introduces a variable when your goal is a function type. So here, and that means it could be a dependent function type, it could be a regular function type, or it could be a for all type, which is also a dependent function type. So here, our goal is for all A, B, C, A equals B implies A equals C. So we're going to introduce A, B, C as assumptions using intro. And then we're also going to introduce these two implication assumptions. So that's what happens here. And they all become named, so we give it the names of the things. So this is the term mode equivalent is fun, right? Like that. That's the same.
I guess the reason it takes so long to build the first time is because it's building mathlib.
It shouldn't, and that was the thing I mentioned at the beginning. So
It's fine.
Let
It's
me-
almost done.
no, so if it looks like MATLAB is building, then you should just kill it, run like exe cache get, and then and then restart lead server, and then it will be done.
Oh,
So that is
But
needed
I
on
guess
each.
if you're almost done, I guess just wait.
It's very unlikely that you're almost done. Like this will be almost, unless you're like 97% done.
I'm at
But maybe
2,000 or 2,100 out of 2,500. So
Yeah, you're halfway done.
So
That's
this is
someone
run
on
on each
the
repository that is Lean based, like the one from the course in mathematics on Lean. You have to run this on each one. You can't do it once for like.
So Lake exe cache get will unpack cache files into your current project directory.
Okay, so
There will be a copy of mathlib in all of your projects if you have multiple projects with which depend on mathlib, but they will be sharing the same cache files, so it's not like it has to re-download the same things unless they're depending on different versions of mathlib, which is quite common.
So in different repos you should run it like always.
Yeah, you should run this like exe cache get, and then you can just do your stuff, and you can run the build multiple times. But then if you want to change your mathlib version, or if you're moving to another computer or another folder which doesn't have mathlib, or if you decided to remove your .lake folder because things were weird and you just wanted to reset, then you'll need to rerun this.
Back to my previous question. So then first, basically applies try implicitly to everything.
Not exactly. First applies the first tactic, and then if it fails,
it's like
it
resets second
resets
state.
and then tries the second one.
Okay.
And then if the last one fails, then it fails with the error message thing.
how do I kill the build?
There's probably a lean, if you do lean stop it.
yeah, I was just thinking to myself, I was like, this shouldn't happen for everyone who uses Lean. Like there should be like a cache flag, it's already been built. So.
Yeah, there's a lot of engineering that went into this cache. Use it.
But yeah,
It's,
apparently not sufficient engineering that got into the language server. to
Yeah,
tell
well,
you to use
this has to do with politics.
Yeah, I guess.
This is a mathlib tool, it's not a lean tool.
Ah, okay.
I guess I should have just read the wiki.
Do we have a neo thing to pinch? Or?
Yeah, I mean the InVim thing was pretty easy to set up, so I used it.
So, let's start file and see if no, it didn't. Oh, stop.
Neo thing we have looking for tabs.
How do I get the
Okay.
inspector?
Yeah, it's processed.
Like how can I case on an expression also get the equation that the expression is equal to the pattern and the branch? Like for instance, if I do case f of x and then I have cases true and false, I want to know
Oh, I see.
in the branches that what I
So you're
case
saying
over.
if I have, actually, let me put this somewhere reasonable. Where was it? So. So you can pattern match on f of x, and you'll see that like the the goal here was f of x equals 0. After the pattern match, it becomes 0 equals 0. But you would like to have an equality that says like f of x is equal to 0. And the syntax of that is this: you write e colon or whatever the name you want, and then here we have an assumption f of x equals 0 in this branch. and f of x equals n plus 1 in this branch.
Okay. Thanks.
And typex also work on non-prop types.
Yes. Yeah, so I could do something like this.
You have how many classes and after will be presentation of it. Everyone.
I think you should have said
Yeah. And we will have a lot of classes and after will be a lot of days of presentation.
There will be, well, days at least of working on your projects, and I will probably be doing some kind of individualized meetings with people
Okay.
about their projects and stuff like that. We might have a presentation at the end, I don't know.
Are the projects basically like proving some specific mathematical?
Yeah,
Like
yeah.
that.
So the goal is going to be like, you know, find something that is interesting to you and do some non-trivial formalization in English.
Can you give like an example of what's a typical? Well, so what would be expected as?
I mean, well, in terms of lines of code, I'm expecting somewhere in the range of like, you know, maybe 500 to 1,000 lines of code. Proving, I don't know, some irregularities and regularity. I'm not sure I can give an example that's at the right, you know, it depends on your specific area.
Because I see in the mathematics book there's stuff like with topology and filters and stuff, and there's like some pretty.
Yeah, so I mean, MATLAB is quite. We haven't actually explored MATLAB very much yet. So far, all of this has been just bare bones lean stuff. But MATLAB has a ton of stuff already, and so it's not that unreasonable for you to make some real, you know, like if you're building on top of MATLAB, then it's much easier to go a little bit further. But you're going to need to know what's in MATLAB, and so some part of assessing the project is going to be like figuring out what is in MATLAB, what's the next, you know, thing that we can do that's going to be interesting.
I still get the imports are out of date error. So am I supposed to press this one?
Yeah.
Now that I have run
Yeah,
this.
once you run that, then
Okay,
it should.
okay. Oh yeah. No, now it's building.
Wait, give it. Yeah, you're right. It's not good.
Wait, so what happened when you run like?
No files to be downloaded, it says because I already run it.
I'm not sure. I'm not sure.
Wait, can I look at this version?
Yeah.
Is there a tactic for repeat 5 times or like repeat n times?
It's called iterate.
Very exciting.
So iterate 5 in place of repeat.
Thanks.
Okay. I guess the people who left aren't planning on coming back, so let's continue. Okay, so now I'm going to tell you about rewriting. So rewriting is a pretty big aspect of how Lean works. This is implemented at the term level using just equality substitution and other, well, we can actually look at what it does. It's somewhat hairy stuff. So you're probably going to want to use the rewrite tactic. But I can tell you what the rewrite tactic does by just sort of looking at some examples here. So here we have a goal that says f of k equals 0, and we have a hypothesis h2 that says that k is equal to 0. When you use rewrite, the rewrite tactic, or RW tactic, you give a list of things and it's going to apply them one after another. So here, it's going to apply h2 to the goal. So that is to say, it's going to look for the left-hand side of this equality, which is k, in your goal. So it's going to find this k here, and then it's going to replace it with a 0. So after this, the goal becomes f of 0 equals 0. Okay, so that's basic rewriting. And we do that again here. We have a hypothesis that says f of 0 equals 0. So we rewrite, and then it becomes 0 equals 0. And then rewrite will automatically close the goal if after the rewrite it has turned into a reflexivity thing. So the goal is done. So that's rewriting. And you can either write it one at a time like this, or you can write it as a list. These two do the same thing. And you can see it rewriting first f of k, and then f of 0 goes to 0. It also works with composed terms. So here, h is a conditional equality. So it says x equals y, assuming that q is true. But I have a hypothesis hq that q is true. So if I apply h to hq, then I get x equals y. And so I'm going to rewrite with x equals y. My goal is p of x, so I find the x's, turn them into a y. And so rewrite reduces the goal to p of y, and now assumption closes the goal. You can also use conditional rewrites without sort of finishing them. Like you can, in this case, I'm rewriting, so I have p of x, but I gave it something that's not an equality as an argument to rewrite. I gave it this implication. So what it actually does is it sort of peels off these implications, and then it rewrites with the left-hand side of this equality. So it looks for x and replaces it with y, but it still has this q. In order to do that rewrite, it needed to know that q was true. So q gets sent back as an additional subgoal. So now we have two subgoals. One of them is p of y, which is our sort of main continuation, which we close with assumption, and then the second part is our sort of side goal. Okay.
It's when you hover over the RW, it says RW is like rewrite, but also tries to close the goal by cheap, reducible, powerful actors.
Yes, this is not a very good comment. So rewrite also exists and has much more information that I would like to have written on the RW tactic as well, because RW is used way more commonly than rewrite. And as this docstream says, they are technically not the same. Rewrite does this thing where it closes the goal. So I showed this example here, where I did rewrite, and then nothing, and then the goal was closed. And that was because the last thing after the last rewrite was 0 equals 0. If I use rewrite, it will just skip that part. It will give me a sub-goal, and you can see we're not done yet. It gives me back this reflexivity, so I have to finish it with REFL. And so rewrite is, or RW tactic is do rewrite, and then if the goal is a really easy REFL, just close the right. But if you want to know all of the things that rewrite can do, and RW has exactly the same syntax as this, you should look at this doctrine. So you can rewrite backwards. So here I have f of b is in the goal, and I want it to be turned into an f of a, and I have a equals b. So rather than rewriting the left side to the right side, I want to rewrite the right side to the left side, and I do that by using a back arrow here before h1. So rewriting with h1 isn't going to work because there's no a's in here, but there is a b, and I can replace it with an a. And then h2 is going to rewrite f of a to 0, and then we're done. It can sometimes be the case that rewriting, so what it tries to do is it finds the first occurrence of the thing that you want to rewrite with. So here I want to rewrite with associativity of addition, right? So there's actually two places in this goal where we have two pluses in the right arrangement. And you'll notice that it's decided to rewrite the left one. Why did it do the left one? Well, it just does a top-down, left-right search for the first matching subterm, and then it rewrites all occurrences of that subterm. So in this case, it finds a plus b plus c and rewrites it to a plus parenthesis b plus c in the expression. But sometimes that's not what you want. So in this case, if we rewrite with adcom, let's say I wanted to rewrite, in this case, I'm trying to group a plus b plus c equals a plus c plus b. So I want to swap the b and the c. But I can't do that immediately because they're associated the wrong way. So first I have to associate them, flip them around, and then associate it back. When I try to rewrite with adcom, thinking, I'm going to flip the b plus c to c plus b, that's not what it does. Instead, it decides, I want to flip this plus, right, the a plus b plus c, and so we'll flip that around to b plus c plus a. And that's not what I wanted. So one thing that you can do is you sort of specify this goal a little bit. So instead of using adcom of anything, I'll say adcom where the left argument is b. And I'll still leave it up to rewrite to figure out what the right argument is, so it'll look around for where is there a b plus something. And in this goal, the first occurrence of b plus something, the only occurrence of b plus something is this b plus c term. So I get my b plus c getting replaced as I wanted. So that's one way to do this, and here's another version where I do add assoc twice, and then I have to do this flipping, and so on. Here you can also, specify the second argument instead of the first one. So this hole gets filled in by C, and it just figures it out based on what is in the goal. Okay. So you can also rewrite in hypotheses using this @h syntax. So here I have a hypothesis that says a plus 0 equals 0, and I want to rewrite the a plus 0 to just a. And I can do that by rewriting using @0 @h, right? So that's what that does. And now I have a hypothesis a equals 0, and I can use that for rewriting. So if I did the rewrite originally, it would say I can't do it because I don't have an a plus 0 in my goal. I just have a. But if I first rewrite h, then I have a equals 0. Now I can rewrite with h to finish the goal. And here's another example of using tactics to rewrite non-proofs. So tuple here is it's a list with a given length, so like a vector kind of type of, or what do you, so we want to rewrite using this n equals 0 on a tuple of length n to get a tuple of length 0, and we do that by rewriting h at t. So this is just basically exactly the same as we've been doing before, but tuple here is a type, it's not a problem. So. Okay, so simp. So simp is like rewrite, but it's a lot more sort of automatic. Here's a basic demo where I have this whole long thing, x plus 0 blah, 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 equals x times y, and I can just hit it with simp and the proof is finished. What happened? Well, I can actually, so this can be used in two ways. You can either use it to close a goal, like this, or you can use it to simplify a goal without closing it. So in this case, simp got rid of the x plus 0 and all of this junk and just turned it into x plus y, and which happens to be my this hypothesis h here. So in order to understand what simp did, or sort of make it more low level, we can use simp question mark. So we put the question mark on simp, and it gives us a try this that says exactly all of the things that it used. So we replace it with that, and we can observe that it still works. And so it's saying, well, I simped with add 0, mul 1, 0 add, and mul 0. So these four lemmas were applied as rewrites. And we can actually work out that, actually that works. If I use these four things, possibly repeatedly, just using rewrite, so I can replace this add 0, and then there's a mul 1 here, which simplifies into mul 0 add, and then mul 0 here, and then add 0 again. So this is the second time we've used this one. And now we have x plus y, x times y equals x times y, and that finishes the goal. So basically, simp is saying, well, I know all of these lemmas. They've actually been added. So if we look at the, oh no, let's not look at that. Are there examples? Close enough. Let's just pretend this is simp. These lemmas have been marked with simp, and because of that, they've been added to a sort of global registry of lemmas that will be used for simplification. And ultimately what that means is that simp acts like rewrite, where it just rewrites with all of the lemmas in this database until nothing more makes progress, and then it stops. So there's a lot of work that goes into sort of maintaining that database, keeping it sort of confluent and having other good properties of a rewrite system. But the upshot is that you can sort of prove goals like this automatically, and you can simplify goals like this. Here's another example using stuff about lists, where we've just killed this goal about XS plus, so what is even happening here? So reverse of an append, so this is XS append 1, 2, 3 as a list, is the same as 3, 2, 1 append reverse XS. And this is because there's a lemma that says reverse of append is you append the reverse of the two things but in the opposite order, and then reverse on cons is the same as append in the opposite order, and so on, and then append applied to a cons reduces, and so there's just this whole long string of reductions that occurs. We can probably look at this list of stuff. So we have like this reverse append, reverse cons, reverse nil, and all of these have been marked as simp. And so this allows simp to act as a kind of partial execution engine even, to be able to work out like what happens when you reverse 1, 2, 3, you get 3, 2, 1, and they can just be proved automatically by simp. Here's a slight variation where it doesn't finish the goal, but what happens is that reverse on append, as we saw, gives us append of reverse. Length on append is the sum of lengths, and those are both set as simplemmas, but commutativity of addition is not a simplemma because it would loop asterisk. So if we wanted to finish the proof in this case, we just give it net adcom, and you can see that it went from this almost solved goal where we have it's simplified away all the stuff about appends. We just have ys plus dot length plus x's dot length is the other way around. And if we throw in adcom, now it knows everything it needs to do in order to finish the goal.
So is it kind of just up to your intuition to know what are simplemmas and?
Well, so basically, there's a library-wide maintenance of a concept of simp normal form, and then there's a bunch of reduction rules that lead you towards this normal form. Some things are just sort of obviously simpler, like x plus 0 equals x. That's a very safe rule to just simplify whenever you see it.
Yeah.
A less safe rule would be something like this De Morgan, or not De Morgan, I keep forgetting, distributivity rule. Like this one here, you could imagine this being simple. Whenever I see this, I'll simplify it to this. But then also if I had the other rule for and over or, then it would just exponentially explode, so I probably don't want to do that. In general, this, we call these non-linear. No, I don't know whether that's the right terminology here. But they're using a variable more than once in the output. So this is going to potentially exponentially grow the size of the term. These are slightly dangerous to use as simp rules. But
could you have a simple rule the other way around? That if you have like a p duplicating the left hand side to turn it into.
Yes, but for various reasons that might not trigger as much as you would like. It's quite common that it won't be exactly the same p in both cases.
Could you have commutativity and sort alphabetically by variable name or something like that?
Excellent question. That comes to the next part. I said that, to first approximation, simp takes all the lemmas that you give it and all the lemmas that have been marked, and then it rewrites with all of them until things stabilize. But this would do bad things when you give it something like adcom, right? If you rewrite with adcom, you're going to get another thing that you can immediately rewrite with adcom again, and you would diverge. Simp does not solve most of the instances of this problem, but it does happen to handle specifically for commutativity functions. So like, if it's a function f of xy equals f of yx, it will specifically detect that and then use it as part of a ordered rewrite system. So there's this magic sequence of 3 lemmas that you can give it for for doing commutative associative simplification. So if I give it add a sock, so here we have left associated to right associated, add com, which does commutativity, and then add left com, which is a consequence of add sock and add com, but we need to give it explicitly as a simp rule here. And what this does is, given a right associated sum, it's going to swap the 2 left things. What it will end up doing with that is it will first use add a sock to rewrite everything until it's all left associated. And then it will use add left com and add com at the end to basically bubble sort everything else. And so you'll end up with the ordered sequence of inputs, and it'll put things into a normal form. And the reason it does that is because it does use term ordering in order to say, I won't rewrite with this thing if it looks like it's not going in the right direction. So in this example, I set all of these things as local simp rules. And now if I rewrite with them, you'll see that this product has been moved to the right side, and it's also been associated, and it's also been put in alphabetical order. And because of, so these things, they have the opposite order, and in sort of random permutation, but doing this rewriting puts them both into the same form. And because they're the same form now, I can just use assumption and they match with each other. And if it didn't use a consistent ordering for this, then it wouldn't work.
Okay.
And here's another, I think this is just another example of rewriting everything into sort of canonical form, like here, z times x gets rewritten to x times z, so that now, after simplifying everything, lots of things match together, and we can just use constructor and assumption.
So you could think of I mean, it does simplify, but more like a normalizer at the same time. So
Yeah,
you have
yeah.
a sort of like
Yeah,
generic library-wide, like, okay, this is our usual function for normalizing things.
Exactly.
So you kind of know what to expect. Okay.
exactly. Yeah, describing what is simp normal form does need a whole bunch of stuff because there's tens of thousands of simp lemmas in the
Right.
library, and it involves like every, constant that is declared in the library. But there, you have some general heuristics regarding like, well, it gets simpler and like things get unfolded. When you have a function defined by recursion, it's probably going to simplify when applied to constructors, these kinds of things. And yeah, so you can use AC rewriting in order to solve all sorts of problems of this variety. There's a few more options. You can pass a definition to simp in order to say unfold that definition. So here, the goal has an f in it, and I want to say unfold f, so it will turn that into n plus m. If I didn't do that, I get stuck at f01, because there's no simp rule that tells it what to do with f. But if I have these pluses, then it will know things like add 0 and add 1 and so on. And then also we have these hypotheses h and h prime, and just like rewrite, we can use a back arrow in order to say rewrite the other way around. The star can also be added into this list. Star means rewrite with all local hypotheses. So h1, h2, and so on in the forward direction. This is using that AC rewriting set in order to simplify, I guess, x and w, just rewrite x's and w's away, and then it's up to us, like if we don't do that, then, I guess we didn't need that. Another thing you can do with simplification, which you don't immediately think of as a simp task, is you can prove propositional theorems rather than having to do the whole if intro and the long proof that I showed you before. You can actually kill a lot of these proofs just using simp rules. So yeah, like without any assumptions, you'll see that P and Q, if and only if Q, get simplified to Q implies P. Those are equivalent. And that's just because there's a rule specifically teaching simp about that fact. But if we rewrite with P, what it's actually going to do is find occurrences of P and replace them with true. So all of the P's become trues. And then it has another rule that says true and whatever is equivalent to just the second thing, and then so we did get Q if and only if Q, and then there's another rule that says Q if and only if Q is equivalent to true, and then if simp is able to reduce everything to true, then it just closes the goal pair. So we can actually maybe see that it has indeed used true and. What is true and? This is this statement here, true and P is equivalent to P, and it used that to rewrite the hypothesis. So it first rewrote P to true, and then rewrote with true and then it closed with round. And I think it's doing something similar here. It's going to rewrite P to true, and then it knows that true or is just true. So that's how it closes this goal. And more of the same. Simp has a ton of options. I, have not even begun to scratch the surface of all the things that you can do. with sim. In this, one of the things that you can do is you can simplify using hypotheses that are introduced in the course of descending to a subterm. So that's this contextual option. There are a ton of more options. This is just to tell you that the syntax exists and there are a bunch of options. Look it up if you're interested. Okay, and I have a brief example here of calc, which is another version of rewriting. So this is, let's say, a human-friendly presentation of rewrite root. So rather than just doing rewrite, you can actually say this is equivalent to that, which is equivalent to that, which is equivalent to the thing I want. And so, mathematicians will recognize this from the textbooks. And then there's this random stuff over here, of course, because we have to deline how these things happen. So this is basically a transitivity chain. So here we want to prove D is equal to C plus A, which we do using, H2. Here we want to rewrite the A to a B plus 1, and we do that by rewriting with H1. And then I guess here there's several things we want to do. We want to rewrite E on the right. So you can see in this sub-goal that we're proving the previous right-hand side is equal to the new right-hand side. And we can rewrite on both sides of that. We don't have to be rewriting the right-hand side. We could also be rewriting the left side. But here we rewrite E to B plus C, and then swap some things, and then associate. So that's an example of just doing some rewrites, and then also showing some intermediate stages. This is a more mathematically interesting example where we have a group, and there's a bunch of hypotheses here, or a bunch of theorems that are true about groups that we're going to need. We want to prove that in a group where every element has order 2, it is commutative, so y times z equals z times y. And the way we can do that is by showing that both y times z and z times y are equal to this particular expression here by doing some rewrites. So here we can reassociate this y times z just to get these together, and then rewrite with, so y times z is an instance of this x times x, so we can rewrite with h, and it becomes 1, and when we simplify that, we get y times z. But we can also reassociate this in a different way where we get the y times y together, so we associate that, rewrite with that, so that becomes 1, and then get rid of it. And do the same thing over here. So we have z times z, get those together, and then rewrite it to 1. And now I have z times y, right? So this expression, when associated in two different ways, gives us both y times z and z times y, and when we rewrite with both of them, we get the result. So that's just some example of how to do rewriting. The last part, I just want to give you a smattering of examples of sort of heavy hitter tactics. So these are still relatively manual type tactics, but there are also tactics that are used for implementing certain decision procedures, and they will basically just cover all problems within a given subset of things. So for instance, the ring tactic will prove any statement that is true in the language of commutative rings, of unknown characteristic. So here we have, well, it can handle associativity and commutativity of multiplication, no problem, but it can also handle things like we have expanding a binomial. So this is a plus b squared is equal to a squared plus 2ab plus b squared. And ring basically just expands everything out and sees that they're equal. Or this identity here where you say a plus b times a minus b, that's the same as the difference of squares. And you can work it out using a bunch of applications of like mol-add and molsoc and whatever, but it's just a lot of work, and Ring will just do it automatically. It won't work in this case immediately because it has here we have hypotheses about C and B, but we can rewrite with C and B in order to get it into just a pure equation, which then Ring is able to prove. Another tactic of this kind is linearith. So linearith handles equations in linear, so you can do not multiplication, but addition of and scalar multiplication of like rational numbers or other linear orders, I think, and then less and less equal. So here it's being used to just do a transitivity chain. We have A less equal B less than C less equal D less than E, and then we want to conclude A is less than E, and linearith knows that. But you can also do it with numbers in the mix, right? You have 2 times A is less than or equal to 3 times B, and so on. And so this is actually a somewhat complicated algorithm. You need to have a simplex algorithm in order to implement the full strength of this decidable theory, but it can be done, and there's an implementation. Here we have exponentials. Now, linearith can't completely handle exponentials because they're not linear, but if you give it this fact about, in this case, we just need to know that the exponential of b is less equal to the exponential of c, given that b is less than c. So we hand it this assumption, x to the x, applied to h, and then linearith is able to prove it. And there's another version of, I want to say it's a version of linearith, that's not entirely true, but it's called omega. Omega has more and also fewer capabilities. It can handle non-linear, is that true? I don't think it can handle non-linear, but it can handle quantifiers, and linearith can't. And it can, but it can only work over the natural numbers. So it can handle things like divisibility on the natural numbers, which linearith doesn't understand. But it's also, and this one is also available in Corley, whereas linearith is a math thing. Okay, so there you have it, a bunch of things in your toolbox for writing tactic proofs in Lean. So we'll be meeting next Thursday. Next Tuesday we will be off. So that's it for today.